Hi everyone, my name is Kamoltat. Some of you may know me by Junior, and today I'll be talking about supporting free availability zones in a stretched cluster. Today's agenda, I'll be introducing and talking a bit about myself and the problems with traditional stretch cluster setup, how stretch mode solves these problems, and how the journey of expanding that to three zones, what are the current limitations, and what are the progress of solving those limitations. A little bit about me. I work in the Rails team. I've been a staff contributor for 5 years. Fun fact, that picture was last Sunday. I was in Tahoe skiing. Yeah, really nice place. Recommend you guys going there. Key contributions. So I've contributed to the stress cluster and Power Scaler and some of the SolidWorks tool. So what is a stress cluster? Well, I think for me, stress cluster is a subcluster that has a bigger failure domain. So basically, instead of your failure domain being just OSDs, hosts, racks, it becomes a data center. And instead of being behind a LAN, local area network, it becomes behind a WAN, wide area network. With some of the profiles being that it should be able to withstand net split between two data centers, and you can still serve IO when one data center goes down. Usually we have pretty high latency, high speed and low latency between the data centers. And in this talk, I would use a lot of diagrams. And on the right-hand side of the diagram, there will be some variables. So just keep an eye out them, they'll be changing. So in this cluster, basically you have a size of 4 replication, so 2 replications on each site, and minimum size of 2, with the quorum being in all of these monitors across DC1 and DC2. And I use an example of PG 1.1 with the acting set of 0, 1, 3, and 4. So those are the OSDs in the acting set. So in order to understand how stretch cluster deals with net split or basically disaster recovery, you have to understand a little bit about monitor elections. And we have this strategy in how we elect the leader of the monitor called connectivity election strategy. What it does is that it stores each monitor's connection scores. So each monitor stores connection scores with its peers. It gets shared to all the monitors. Monitor with the highest score wins the election, becomes the leader. If the score is tied, then you pick the monitor with the lowest. So here's a visual representation of how it works. So let's say monitor A and B are competing to be elected the leader. And you, in monitor A's point of view, you have the connectivity scores of itself, what it scored for B and C, and you have all the scores of its peers as well, what monitor B thinks. And so an easy way to calculate that is you take the average of monitor A's score based on what its peers thinks monitor A scores. So monitor A scores 0.96, and the same goes with monitor B. So what monitor B's peer thinks it scores is 0.56. So here, monitor A wins the election. There are two things with like traditional setup with stretch cluster. One of the things is net split, and the other thing is peering rule. So there are two things I would like to remember. So in this traditional setup, when there's net split between DC1 and DC2, the monitors, let's say monitor A proposes itself as a leader, it will only receive the votes from the monitors in DC1 because it can only communicate with the monitors in DC1. And monitor D also proposes itself as a leader, but it can only communicate with the monitors in DC2. So here, because in order to form quorum, you need, in order to win an election, you need the number of votes to be more than half the quorum size. So no one wins in this scenario. So the election cycles forever, and the cluster becomes inaccessible. Next is peering rule. So what exactly is a peering rule? Well, it's a set of conditions when choosing OCs to be in the acting set of a PG. It is crucial to determine whether a PG should go active or not. So whether the PG should accept IO. The trigger rule here is, if the acting set size is larger than or equal to the min size, you allow the PG to go active. And I'm going to demonstrate how this could be a problem. So let's say there's a failure in DC2, so OSD3 and OSD4 goes down. Now the acting set size changed to 2, and it still satisfies the min size requirement for the PG to go active, which is 2. So what happens is that DC1 now can receive IO, so PG 1.1 might have a newer version. But then what happens if DC1 catches fire, and then suddenly OSD3 and 4 gets restored? Now, if you don't recover DC1 at all, you have an outdated version. So this breaks the data integrity of Ceph, meaning we basically have data loss. So how do we solve this problem? And a colleague of mine, Greg Barnum, he wrote the solution, stretch mode. So what is stretch mode? Essentially, stretch mode is you have a extra zone, a site called the tiebreaker site, which only hosts a tiebreaker monitor. It doesn't host any OSDs. And how this will solve the dense split problem. So I'm going to run through the scenario again. Let's say there's a dense split between DC1 and DC2. Obviously, Mon A proposes itself as a leader, and Mon D also proposes itself as a leader. Mon A would receive all the votes from DC1, of course, all the monitors in DC1. Mon D also will receive all the votes from the monitors in DC2. But then, it's up to monitor G to decide, who's going to be the winner. So let's say, well, monitor G is a disallowed leader, meaning this monitor cannot be a leader. It can partake in the election process, but its score is essentially -1. And how it works is that, well, whoever contacted monitor G first will get an outback. So let's say monitor A reaches monitor G, so it responds with a vote for monitor A. So here, monitor A has 4 votes. Monitor D has 3 votes, and so because monitor A has more votes than half of the quorum size, monitor A wins the election. We have a quorum, and the cluster becomes functional. What happens to DC2 is that it will be kept out in the dark because it is not part of the quorum. How stretch mode is set up is that the OSDs can only talk to the monitor in its same failure domain. So that's all the OSDs in DC2 are also down. But at least you have DC1 and DC3 that are operational and can receive IO. Now let's see how a new pairing rule could solve the data integrity or data loss problem. So in stretch mode, we have a different pairing rule called stretch pairing rule. This pairing rule states that an acting set must contain OSDs from both data center 1 and data center 2. So you can't just have an acting set with OSDs from one data center, then that won't allow you to go active. So with this set of new pairing rule, now let's run the scenario again. There's a failure in OSD 3 and 4. The acting set size is 2, which is equal to min size. However, we won't allow PG1.1 to go active because it doesn't have the acting set doesn't have OSDs from DC1. So if there's catastrophic failure and in DC1, OSD 3 and 4 gets restored, it still have the latest version. So no data loss in this case. And stretch mode has a special mode as well called degraded mode. It triggers when all monitors in a data center fails and reduces min size to 1. I know this might not be the best thing, but I think IBM back then has a business requirement to satisfy this. Um, and the peering rule allows the surviving site to serve IO. So DC2 can now serve IO, which is great, but it's still in degraded mode. So stretch mode only works with 2 sites. It's a cluster-wide configuration. So how do we expand to 3 sites? So the first thing that I tackled was make use of the stretch peering rule that stretch mode was using and introduce a new command which allows the user to set the config values for peering rules. So this is a full level configuration set or the full stretch set. And there are 3 variables that I'm going to talk about shortly. The first variable is peering cross bucket count. This is basically the minimum number of distinct bucket an action set is expected to have in order for the PG to go active. So like the example I gave earlier, the peering cross bucket count is 2, so you need at least 2 distinct buckets or distinct data sets in the acting set for the PG to go active. So here is a setup for 3 availability zones. What changes is that now the tiebreaker, you don't have the tiebreaker monitor anymore. Now it's just a third site with 3 monitors, 3 OSDs. Obviously in the real world, this is very minimal diagram for illustration purposes. In the real world, we have more OSDs than this. But yeah, so you store 2 copies in each site. So the replication size is now fixed. The min size is 3, and yeah, the acting set size is also 6. So let's demonstrate how this peering cross bucket count prevents a scenario where we have, the loss of data integrity. So let's say DC1 faces catastrophic failure, there's a fire, and there's a disk failures in OSD 6, 7, and 8. The acting set, let's say for PG1 1.1, it adds OSD 5 due to rebalancing. So the acting set size is actually 3, which, with like a trivial peering rule, you can go active because it's equal to the min size. But here, because we have peering cross bucket count to be 2, you need at least 2 data centers worth of OSDs in that acting set. So it would allow the PG to go active. The next variable is peering cross bucket target. It's a value used in conjunction with size, replication size, to determine the number of maximum OSDs you can pull from each bucket. In this case, each data center. We call that the bucket max. And then why is this important? Because if we ended up losing a data center, we don't want to show off all the 3 data center worth of replica into like a single site. So that's why we have this thing that only limits the number of OC we pull from any given data center to be in the acting set. And the formula for this is pretty simple. So bucket max is equal to the size divided by peering cross bucket target. In words, it means that if I have, bucket max here, we have the size of 6, peering cross bucket target, we should be 3. In words, it means that if I have 3 fair domains of size 6, then what's the maximum number of OSDs I can choose from each site? And the answer is 2. So I'm going to demonstrate how, with bucket max 2, how this would allow us to enforce data integrity. So, the same thing, let's say DC1 is down, DC3 has OSD failures, and the acting set of PG 1.1 will remain only OSD 3 and 4. It will not include OSD 5 because as the peering rule states that the bucket max is 2, so you can only choose 2 from DC2. So now you're undersized and then you can't go active. Okay, so we have solved the stretch peering rule in 3 availability zones. The next thing that I'm still currently working on is how we can expand net split And let's look at the problem with net split in 3 availability zones. So let's say there's net split between DC1 and DC2. And OSD3 reports that OSD0 is down. OSD4 reports that OSD0 is also down. The leader monitor will mark OSD0 as down, and this value can be configured. It basically, by default, I think if there are 2 reports of an OSD being down, then that OSD gets marked down. But then, on the other side of the cluster, you have DC3 reports that OSD6 reports that OSD0 is actually up, and OSD7 reports that OSD0 is actually up. Then the leader monitor then marks the OSD0 back up, which is very confusing. And this vicious cycle continues endlessly, and the PG gets stuck in peering, and so it cannot go active. So you might think, why can't we just deal with this by having a tiebreaker monitor? Well, by designating one of the 3 data zones as a tiebreaker reduces the zone's importance. So it kind of defeats the purpose of having 3 availability zones. So I broke down the solution into 2 things. First, we need to detect net split, and second, we have to make a decision on which zones we choose to survive. And this net split detection feature is already open a pull request for it. It's currently under review. Hoping to get into the T release. So basically, this feature builds a network graph structure, and piggybacking on the existing connection scores we have from the monitors, we can map the disconnection between the monitors. Now, we have locations of the monitors, so we can also aggregate these individual disconnections, and we can make sense of whether all the monitors from the data center 1 is disconnected with all the data center and all the monitors in data center 2. So you would report a whole location net split, but if only partial connections in the monitors, so let's say only some monitors in the data center 1 cannot talk to some monitors in data center 2, you will report an individual monitor disconnection. So it would say something like net split detected between 1A and 1B. Next is right now it's a proof of concept, but how do we pick the surviving sites? Well, I think there are some heuristics that we can take into account. So whether we choose one site to be the survival, it should depend on the number of OSDs in that site. So it prioritizes data availability and minimizes recovery. You should also think about the monitor count. If there are more monitors, it means the quorum has more resilience. Think about connection scores. You prefer sites that are more reliable in terms of communications. And if all of those are tied, then we probably have to have something that will make a decision. We can pick the lowest combined monitor ranks. So how would this look like? So let's say there's net split between DC1 and DC2. The heuristic calculation determines that we should choose DC1 plus DC3. Well, that's because the OSD count, as you can see, that the combined OSD count between DC1 and DC3 is greater than the OSD count between DC2 plus DC3. And yeah, so and what happens is that we mark down DC2, so it's kept out of quorum. And if the net split is no longer detected, then the DC2 will stop being marked down and rejoin the cluster. If not, well, DC1 and DC3 are continuing to operate normally. So that's how I'm thinking about tackling the net split range problem in 3 availability zones. Yeah, that's it. Thank you.